Greetings, Earthlings. This should be a quick one today. One horrible detail about cellular respiration that I've always found interesting is trying to figure out what happens to each of the carbon atoms that we started with in glucose. Okay, obviously we know they're going to become carbon dioxide molecules, but at exactly which step does each carbon atom do that? We've seen this figure before, of course, where glycolysis chops the glucose molecule into two molecules of pyruvic acid, one of which has carbon atoms 1, 2, and 3, and the other has carbon atoms 4, 5, and 6. In the pyruvate dehydrogenase complex, the carbon dioxide molecule we pull off is made with carbon atom number 3, and the other two carbon atoms are now part of the acetyl-CoA. In step 1 of the citric acid cycle, the carbon atoms that come to the party as part of oxaloacetic acid are shown here in blue. So from this point on, we have blue carbon atoms and black carbon atoms. In step 4 of the citric acid cycle, the carbon dioxide we lose is actually made with blue carbon atom number 1. The carbon dioxide that's liberated in step 5 did come from the original glucose molecule as black carbon atom number 2. The black carbon number 1 from the original glucose molecule is now in the same position as what had been the blue number 1 carbon from oxaloacetic acid. Here's the big wheel of chemical pain and suffering again. Starting with the pyruvic acid molecule containing carbon atoms 1, 2, and 3, in step 1 we add the acetyl-CoA to the oxaloacetic acid to make citric acid. Steps 2 and 3 rearrange that to make isocitric acid. Step 4 liberates the carbon dioxide with carbon atom number 1, the blue carbon atom number 1. Step 5 liberates the carbon dioxide made with the black carbon atom number 2. Steps 6, 7, 8, and 9 still have black carbon atom number 1 in the oxaloacetic acid molecule. It's sitting there ready for the start of the next round of the citric acid cycle. Well then, for the next round of the citric acid cycle, the new molecule of acetyl-CoA is shown with red carbon atoms. The oxaloacetic acid we're starting with this time has 3 blue carbon atoms and 1 black carbon atom, so our new molecule of citric acid has 3 blue carbons, 2 red carbons, and 1 black carbon. This time the carbon dioxide we liberate in step 4 is black carbon atom number 1, which came to the party on the first acetyl-CoA molecule. And the carbon dioxide we liberate in step 5 of round 2 is red carbon atom number 2, which came to the party on the second acetyl-CoA molecule. At the end of round 2, the number 1 carbon on oxaloacetic acid is red. In each round of the citric acid cycle, we got rid of 1 carbon dioxide from this acetyl-CoA and 1 carbon dioxide from the previous acetyl-CoA. The oxaloacetic acid ends up with a new number 1 carbon each round, which it got from the newest acetyl-CoA that arrived in step 1. It's pretty much the same story when we start with the pyruvic acid molecule having carbon atoms number 4, 5, and 6. Here we lose carbon atom number 4 in the pyruvate dehydrogenase complex and carbon atom number 5 in step 5 of the citric acid cycle. Carbon atom number 6 then ends up in the number 1 position on oxaloacetic acid, heading into the next round of the citric acid cycle. Okay, that's it for now. Next time, we're going to start introducing different nutrients into cellular respiration, things other than glucose. We just had to go through all of these horrible details for however many videos now for glucose. Do we have to do all that again for all these other nutrients? Good news, no we don't. Anyway, we'll start talking about those details next time.